of the results from the JCMT BISTRO survey. I've tried not to tell you all of the conclusions in the discussion section, but hopefully quite a lot of the introductions have already been done for me, which is great. I do, however, have to introduce the BISTRO survey itself if you haven't already heard of us. We're a JCMT large program. We're mapping galactic star-forming regions at 850 and 450 microns with Pol 2. And there's quite a big project, about 150 people across the whole many partner regions of the East Asian Observatory. And although we started out specifically looking at very nearby Gould Belt-ish regions, we're gradually extending outwards in distance, firstly to massive regions within 2 kiloparsecs, and recently we've started mapping to the galactic center. So if any of those regions interest you, then I'd encourage you to look up the papers that we've got out so far. But I'm specifically going to be talking about some of the results from nearby clouds, particularly Ophiuchus, Perseus, and Orion. And what we've been looking at is this thing that's come up a few times now about how the behavior of magnetic fields change from large to small scales. And very helpfully, we've had all of the Planck measurements looking at the large cloud scale magnetic fields, which we can compare our own results to. Now, Pol 2, or indeed any submillimeter instrument below the atmosphere, is very strongly constrained to look at high column density structures. Most of the extended emission is filtered out just by virtue of being below the atmosphere. So we're strongly selecting for structures that are high column density and, if not gravitationally bound, quite possibly on their way to being so, which does give us a useful discriminant to have some idea what we're looking at. But on larger scales, what's been seen over the last few years is this sort of bimodality. Fields have a tendency to preferentially be either parallel or perpendicular to the major axis of clouds. And it's possible that then respectively either hinders or promotes the formation of supercritical gravitationally unstable filaments. The example cloud that I'm showing here is Ophiuchus, which I'm going to mostly be talking about. And in Ophiuchus, recently, just in the last few months, the Herschel observations of this region have been published by Bilal Lajalati. And what they show when they pick out the filamentary structures, which you can see with Herschel, but you really can't see very much with ground-based instruments at these wavelengths, is that the filaments embedded within the larger clouds are themselves preferentially either parallel or perpendicular to the large-scale magnetic field, very strongly bimodal distribution. So, I mean, the bimodality on large scales suggests some role for the magnetic field in cloud evolution. There's all various Planck measurements suggesting that we've got subcritical magnetic fields on large scales, at least in these lower mass star-forming regions. And these Herschel results again suggest that if the filamentary structures are forming with preferential alignments with respect to the magnetic field, again, the magnetic field is still quite important in the dynamics in the evolution of these clouds towards gravitational instability. But then what happens when you get down to the really small, actually gravitationally unstable scales? Well, I mean, logic suggests that if we can form stars at some point, we've got to lose this subcritical magnetic field behavior. We've got to get to gravitational instability somehow. And a lot of the recent numerical simulations, I've picked out some of Daniel's work from earlier this year here, are showing that there is if you start out with a field if you start out with a filament, a cloud with a magnetic field that is parallel to the cloud direction, it will flip to become perpendicular to filaments at high densities. In this simulation, I think the flip was to around about 10 to 3 particles per cubic centimeter. And that transition, flipping from parallel to the cloud to perpendicular to the dense filaments, is indicative of a transition from magnetically subcritical dynamics at low density to gravitationally dominated dynamics at high density. So of course, we wanted to know whether we can see this sort of thing in our own data. And the cloud that I've mostly been looking at recently, this is results that have just been accepted, the papers on archive at the moment, is L1689 in Ophiuchus. So Ophiuchus, it's both great and terrible to look at because it's so nearby. We can see far too much detail, studying sort of clump by clump, core by core, what's going on. And it's a site of low to intermediate mass star formation. And there's the two main clumps, L1688 and L1689. And L1689 is a good one to study just because it's a bit more quiescent. There's no B stars providing feedback as there are in the L1688 clump. And it does have some active and ongoing star formation, particularly it's hosting the very well-known IRS 162932422 protostar. So we pointed POL2 at three different clumps in this region, L1689N with the protostar and two starless cores and clumps, L1689B and SMM16. And what we found is that the magnetic properties of the three clumps are actually surprisingly similar despite their different star formation histories. Even though we've got one star forming in two starless clumps, in all of them we get approximately transcritical, possibly slightly subcritical, but it's the GCF method, so we've got large error bars. Oh, 3 minutes already. Right, I'm going to talk faster. We see approximately transcritical and subalfenic magnetic fields in all cases. However, in IRS 16293 and L1689B, we've got alignment with a large-scale field, but in SMM16, despite the fact it's not very gravitationally unstable, the field has been twisted by 90 degrees relative to the large-scale Planck field. So what we found is that in every case, the clump magnetic field directions are determined by the orientation of the filament in which they're embedded and don't seem to have any particular connection to the large-scale magnetic field direction. So it seems like this transition from large-scale magnetically dominated to gravitationally dominated has happened at or near the densities that we're looking at with POL2. But this is despite the fact that the filaments aren't themselves gravitationally unstable. They're at most marginally unstable, and we're measuring transcritical mass-to-flux ratios. So it seems like with POL2, we're very close to being able to catch the transition from sub to supercritical gas dynamics in these nearby clouds. Looking slightly further away now, at about 300 parsecs, this is work that's recently been published by Yasuo Doi. We're now seeing more of the structure of the filaments themselves with POL2 just by being slightly further back. And what we see is, again, the field that we see with POL2 doesn't necessarily connect very well to what's being seen with Planck. In the north, there's good agreement. In the south, again, a 90-degree flip. So it looks like the large-scale magnetic field has stopped dominating the dynamics at these gas densities. Yasuo Doi, he also did some analysis of the relative orientations of the field and filament in projection and showed that statistically what we see in Perseus is consistent with the field being perpendicular to the filaments in which they're embedded regardless of the large-scale magnetic field direction. Simon Coudet is doing some follow-up work measuring the magnetic field strength, so hopefully we'll have some criticality values, mass-to-flux ratios to put together with this soon, start looking at this more systematically. But finally, I just wanted to flag that we do also see some environments in which gravity has absolutely and definitely won, and Orion A is one of them. We see, if you take a very broad average in Orion A, the field is perpendicular to the filament, but we see in OMC1 this very nice hourglass-like magnetic field structure, which isn't anything to do, as far as we can tell, with the kind of with the kind of classic ambipolar diffusion-related hourglasses that you might see in a secularly evolving clump. This hourglass structure is very much centered on the interaction between these two dense clumps. So our best idea of what's going on, based on energetics analysis and velocity and the velocities in the region, is simply that we're seeing the gravitational collapse of material along the filament, in this case pulling the magnetic field just along with it. it seems like gravity is very much one here. This isn't quite the same thing as Tishara Pillai has seen recently in serpents. They see the field turning within the filament as material flows along towards a central hub, but it's the same general picture. We do seem to definitively reach a point at which gravity has won, and we're seeing it with Pol 2. So I'll just leave my summary up there, and thank you very much for your time.